Hello, nice to meet you, everyone. I'm Nick Sayer. I'm the product director for Ring. I'm going to speak to you about a spatial use case that we developed and deployed for CNES, a part of the European Space Agency here in Europe. CNES had problems. CNES is capturing data and information from multiple satellites, about 200 satellites over the world, and getting that information live feed directly into storage and needs to analyze that data to, I was reading on the news yesterday, spot the smoke that's coming from Canada and hitting the coast of France. All of this live data needs to come super quickly, about 10 to 12 petabytes per year coming live. These are satellites going around the Earth. This data is very live and very useful. In the first 6 months, they do analysis, try to understand patterns on how the Earth is behaving, what those satellites are capturing. Once that's done, this data is not really live and useful anymore. You need it, you need to keep it, but you don't need to actively use it. So they wanted a cheap way to put that data aside, to eventually go look at it at a later time for further analysis, try new algorithms to try to understand the sea levels, for example, and how these are evolving. This cold data, this data that's less useful, is hundreds of petabytes. Those satellites have been going around since the 60s around the Earth. As I said, about 200. So you can imagine the quantity of information they need to store and keep available for people that want to look at this older imaging. The other challenge they had multiple storage solutions based on NFS, on file, on SAM, some that were actually attached to some satellite technologies and very difficult to manage and aging. They wanted to go S3 everywhere, a single protocol for all usage of all of their data that's perfectly standard, cheap to use. You have libraries all over and developers available widely to develop on S3. So that was also a big move for them. They're conscious of cost, they're conscious of energy. One thing they said on the first day, having drives thin with data that is 20 years old that I'm eventually going to have to look at in a few years, it seems not optimal in terms of using your energy and getting things moving. So that's something that we're really attached to. Going back to the core requirements, security of data. This is public data, but it's super important that it's not tampered with. Reducing cost, space usage of space of the infrastructure, energy consumption, essentially trying to have the as small as possible infrastructure for the most capacity and leveraging this cold and hot and be sure that we have the proper technical solution for the type of data. And of course, this single protocol and really a single namespace. They didn't want their users, their applications, their public to have to understand, oh, that data is in that here and I have to access it like this. They wanted a single namespace to be able to get the data 20 years ago or a few minutes ago in the exact same way. How did we address this? We built for CNES a ring on 3 sites, as Paul was referring to, allowing you to lose an entire data center and still keep access and security on your data. And this ring serves the hot and warm data. That's where the satellites actually write every day, 24/7. This data is actively consumed by compute engines that analyze that data, enhance the imaging to make it consumable by weather agencies, by military, of course, as you can imagine. Even the public, I can go see NES's data the day after and see my house and see what I need to fix in my garden, for example. It's really high definition. Then this data, after 6 months, is fairly stale. That's where we transition into tape to actually 2 tape libraries in 2 locations. So we have this duplication of information, and we remove it from the hot tier. This transparently, again, from the users and the
I have a question here.
Go ahead.
So you keep everything in object, right? In this single namespace. And then when you move it to the tape drives, what kind of software do you use?
So we built our own solution, which I'll describe in a bit. Basically, we don't manage tapes. That's not our business. So we rely on third parties that have HSMs that have managed tape for years. So we work with EMF from HP, with Atempo. We work also with other cloud vendors, IBM, Spectra, for example, so that they manage tape and the ability to have a an arm move the tape from one drive to the other. We pilot the actual HSM to tell them to stash that object back on tape, to retrieve that object and put it back on Ring. This is completely transparent for users.
Exactly.
From a user point of view, you're using a Glacier API and just putting and restoring objects.
So you build your kind of middleware, right? That it's communicating with API of the tape controller.
Exactly. And I'll mention it in a couple of slides. We call it TLP. It is public in the sense that we build it for a first integration that we did with our partner HP. And that API is gaining traction. We build it with another company here in Europe called Atempo. And we're actively working with new partners to integrate this cold management API. Essentially, it's an API to manage the access to asynchronous access to data that you cannot retrieve on a GET, that you ask to retrieve and get notified when that data is retrieved because you need to move the tape or do whatever you need.
Right. So, and then you leave like kind of a, like it was during the NFS times, like a stub file, but in the object that the user is connecting to, and then it's restored automatically from the tapes, right?
You access your bucket, you list your bucket, you see what's hot and what's cold in that bucket. You have an S3 attribute that will tell you, oh, that data is cold or that data is hot, so that you could know what you could get immediately. And if you try to get an object that we don't have anymore, that's been put on tape, you'll get a specific message back from the AWS API telling you that you need to restore that object. You trigger the restore, then the tapes move around. You can get a notification on that restore, so you don't have to pull every minute, try to see if the object is here. You just wait for the notification. And when that object or multiple objects or bucket has been restored, your application is informed and can consume that data directly on Ring. And it re-expires after a certain and predefined amount of time because you don't want to keep it in two locations. Essentially, it's cold data. So that restoration principle is temporary. That's completely aligned with how AWS Glacier behaves in terms of API.
Thank you.
Thanks. So what's our value proposition here? We have managed cold storage for a few years already, essentially working with Azure Archive, for example, with Glacier. The big evolution is actually directly managing hardware, managing tape through those partners I was speaking about a bit earlier. And that integration we did for them in a way, again, that's completely transparent for the user. Of course, the people at CNES had to set up a tape library, had to prepare all of that infrastructure. Their users, their applications have no clue that there are tape drives, that there are multiple locations or whatnot. They see buckets, they see storage locations for their objects in their buckets. They can ask restores, they could put lifecycle policies. For them, it's exactly as if it was an AWS Glacier with a cost of on-premise local, way cheaper in terms of a cost to petabyte, and way cheaper because you don't have to pay to actually get the data out of your own Ring. A single reference to data, I think that's super powerful. It means you can build very complex, multi-tiered infrastructure in the back of your customers. They don't see it. They only see a single reference and always access an object, an image with the same URL. Resiliency integrated, and especially for CNES. Again, it's public data, but it's super valuable data. That's how we see how our planet evolves. 3-site stretch over 3 data center. You can lose one of them, you can burn down one of them. The data stays available. And those objects stashed on libraries are put on 2 different libraries in 2 locations. Again, to ensure that if an event occurs, you don't lose anything. We also added the security that comes from Core 5 that Paul was mentioning, a strong S3 IAM model to ensure that no one can actually tamper or access the data that he does not have the right to answer. Object lock to ensure that those objects stay immutable and cannot be changed over an infinite course of time. There's no expiration of data at CNES, unlike what Ben mentioned on that bank. Here, the data is kept forever and ever. What's the state today of the deployment? We have a question? Sorry.
Yeah, is there a distinction here between a stretched ring and a replicated ring?
There is a distinction. Yes, a stretch ring. All of your data will be on all of the sites in an absolutely synchronous manner. When you write with your application and you get the acknowledge of that write, your data is fully secured on all of the sites. Meaning you can lose a
It's
site.
replicated in a synchronous manner. Is that what you said? It's synchronous replication.
It's fully synchronous when you're on stretch. When you're going into asynchronous rings, as Ben was presenting earlier, there is a delay between the time your data is written on the first ring and it's available on the second ring. Delay that can be in milliseconds, seconds for sure, maybe a bit longer if you have a big push in terms of data ingest. But essentially, it's asynchronous. So we acknowledge the write once we get the data on the first site, and then in the background, send it to the second site.
And the cold data in this configuration for ESA is also replicated across multiple tape libraries?
It is actually sent to 2 tape libraries. And to be precise, some of the lesser important data, some of the data that CNES did not capture themselves, but comes from satellites that are British, maybe this is only sent to 1 library because the British people have another copy of that data. And the CNES and the data that's purely CNES, all of our own satellites, those 200 satellites, those are written in Y on the 2 tape libraries. And only when we have that right on the 2 tape libraries do we acknowledge this on the ring side and we dereference, we remove that local data and just keep a reference on it.
Okay, thanks.
Welcome. Yeah, summing up a bit, what's the status today? We have about 53 petabyte hot at CNES, just short of 100 servers that are deployed out there. And that's how you access your data in 10 milliseconds or less, depending on the size of the object. Then we move it to tape. They have about 150 petabyte tape. This will grow organically as we have more satellites. We have higher definitions images also. So for Scality, a source of revenue that's going to keep on going, for example. Latency is a few minutes, sometimes due to the specifics of tapes. It could be a bit more. They're looking, for example, starting to take tape out of the library and put them on shelves. And in that case, you need this human intervention to get the tape back. This homegrown API, which we built and invented, adopted by 2 partners today with developments ongoing for other partners. This is really powerful for a product like us to integrate support of tape like this. It's really a big gain for our product. When I started working in the industry, I was told, tape is dead. You shouldn't even look at it. It's still here, and it's actually growing. I'm not quite sure why. The density, the cheap storage cost of tape for sure. The fact that it does not consume any energy when it's not in use also probably helps. And last but not least, 3rd time I'm mentioning it, but it's super powerful. We hide that tape complexity, everything behind that Glacier API. That's where CNES, ESA, and multiple other customers we're working with today are really adoring that solution, is that it's completely transparent to their users.